Before the steel reached the clouds, it lived in the mind of a visionary. Fazlur Rahman Khan didn't just build skyscrapers, he reinvented them. By treating a building like a hollow tube, he defied gravity and the wind itself. It was the perfect marriage of structural logic and soaring ambition. From paper to pavement, his legacy redefined the limits of the modern city. By the 1960s, the skyscraper was dying. Traditional engineering had hit a wall, literally. Past 30 stories, buildings became too heavy, too costly, and too unstable. Enter Fazlur Rahman Khan. As chief structural engineer at SOM, he didn't just tweak the math. He rewrote the laws of physics. He shattered the glass ceiling of architecture, proving that to go higher we had to think deeper. Khan's brilliance wasn't just in his 2 master's degrees or his PhD. It was in his structural empathy. Born in Dhaka to a mathematician father, he learned to see the world through logic. But he felt it too. He famously said, "I put myself in the place of the whole building." He didn't just calculate stress. He visualized the twisting and the strain as if it were his own. For Khan, engineering was a human experience. In the mid-century, height came with a premium that few could afford. As buildings grew taller, the wind became a relentless enemy. Traditional frames suffered from shear sway, twisting like a flimsy grid. To fight this, engineers simply added more steel, but the costs spiked exponentially. It was an economic and physical dead end. To break the ceiling, Khan knew he couldn't just add more material. He had to change the shape of the system itself. Before the 1960s, skyscrapers had a height problem. To go taller, they needed massive internal columns that ate up floor space, yet they still wobbled under wind pressure, a phenomenon called shear sway. Think of it like a grid of sticks struggling to hold its shape. Then came Fazlur Khan's hollow cantilever paradigm. Instead of hiding the strength deep inside, Khan pushed the structural support to the exterior perimeter. By spacing exterior columns closely together and joining them with deep beams, the entire building began to act as a rigid, hollow tube. Under wind load, the Khan tube transforms lateral pressure into simple vertical forces, tension on the windward side and compression on the leeward. This revolutionary shift allowed buildings to reach unprecedented heights with less steel and more open space. It wasn't just a new design, it was a structural rebirth. Why did the Khan tube change everything? It wasn't just about height, it was about economics and utility. Compared to the traditional frame, the tube system rewritten the rules. While old-school frames suffered from shear racking and became prohibitively expensive past 30 stories, the hollow cantilever remained stable and economically viable at 100 stories and beyond. By pushing the strength to the perimeter, Khan achieved the impossible, using 50% less steel while creating wide-open, column-free floor plans. Architects no longer had to design around a cluttered forest of internal supports. This efficiency turned the skyscraper from a space-consuming luxury into the lean, functional backbone of the modern skyline. The tube concept wasn't a static invention, it was a rapidly evolving lineage. It began in 1962 with the framed tube at the DeWitt Chestnut Apartments, using closely spaced columns to create a rigid hull. By 1968, the tube-in-tube design at One Shell Plaza added an inner core for extra strength. The innovation reached a visual peak in 1969 with the trussed tube, seen in the iconic diagonal bracing of the John Hancock Center. Finally, in 1973, the bundled tube was born. By grouping multiple tubes together, the Sears Tower achieved immense stability on a massive footprint. From a single square to a complex cluster, Khan's lineage turned the sky into a playground for structural engineering. Standing at 1,127 feet, the John Hancock Center is the trussed tube in its purest form. Completed in 1968, its signature X-bracing isn't just aesthetic. Those massive diagonal members minimize shear lag, allowing the building to act as a single rigid unit against Chicago's fierce winds. But the tower's greatest strength was Khan's own integrity. During construction, a 14-foot void was found in a foundation caisson. Facing immense pressure from developers to ignore the delay, Khan didn't blink. He halted the entire project to inspect all 57 caissons. This commitment to safety ensured that the Hancock didn't just reach the clouds, it stood on a foundation of absolute trust. How does a building become a hyper-stiffened box? By making the diagonals do the heavy lifting. In a truss tube, those iconic X-braces serve a dual purpose. First, they tackle wind loads, acting simultaneously as inclined members and shear resistors to prevent swaying. Second, they handle gravity loads, redistributing the building's weight evenly down to the corner columns. The takeaway is simple. These braces are far from decorative. They force every perimeter column to share the burden, transforming the skyscraper into a singular, ultra-rigid structure. By optimizing how stress moves through the frame, Khan proved that elegance in engineering is often found in the most direct path. To reach the top of the world with the 1,454-foot Sears Tower, Khan realized a single tube would be too wide and inefficient. His solution? The bundled tube. By grouping 9 separate frame tubes into a 3x3 grid at ground level, he created immense stability against lateral wind forces. But the genius lies in the drop-off. As the tower rises, corner squares fall away in stages. This isn't just for style. It breaks up wind flow and creates that iconic tapering silhouette. Completed in 1973, this 110-story marvel proved that by bundling individual structures, we could build lighter, taller, and stronger than ever before. Khan didn't just build a skyscraper, he mastered the wind. Fazlur Khan's genius wasn't limited to vertical heights. He was equally transformative on a horizontal scale. When tasked with the Hajj terminal in Jeddah, he faced a massive challenge, sheltering 80,000 pilgrims at once across 430,000 square meters. Khan's solution was the cable membrane tensile structure. By utilizing a lightweight fabric membrane as both the environmental enclosure and the primary structural element, he avoided the heavy, labor-intensive grids of traditional construction. This innovation allowed for an immense, unencumbered space that breathed with the environment. It proved that whether reaching for the clouds or sheltering the masses, Khan's mastery of tension and materials could solve the most daunting architectural puzzles on Earth. Beyond the steel and glass, Fazlur Khan operated under a philosophy he called honest architecture. This framework rested on 3 pillars. First, structural efficiency, using technology to do the maximum work with the minimum material. Second, visual coherence, believing a building's natural strength should be expressed, never hidden behind a decorative facade. Finally, and most importantly, social impact. For Khan, vertical density was a tool to ease urban congestion and serve mankind. He famously warned that the technical man must not be lost in his own technology. He believed that engineering must always remain in service of life, of art, drama, music, and people. Khan didn't just build skyscrapers. He designed monuments to human potential. Fazlur Khan began with a math and economics problem: how to beat the height premium that made tall buildings bankrupted by their own weight. He solved it with equations, but in doing so, he inadvertently birthed a revolution. By pushing the structural support to the exterior, he created structural expressionism. For the first time, the bones of a building weren't something to be hidden behind stone or glass. They were the architecture. This new language turned load-bearing columns and wind-bracing trusses into the primary aesthetic features of the modern city. Khan proved that when engineering is honest and efficient, it doesn't just support life, it defines beauty. Fazlur Khan's revolution wasn't a solo act, it was a rare bridge between 2 worlds. In the 1960s, engineering and architecture often sat in silos, but Khan broke that mold through his close partnership with Bruce J. Graham of SOM Chicago. It was a masterclass in interdisciplinary collaboration. Graham provided the bold architectural vision, while Khan brought the structural reality to make it stand. Together, they engaged in a creative exchange that dissolved the lines between their fields. As seen in these rough, hand-drawn sketches, their process was a raw evolution of ideas, turning scribbled concepts into the steel giants that define our horizon. It serves as a lasting reminder that the greatest leaps in science often happen at the intersection of logic and art. Fazlur Khan's journey ended far too soon when he passed away in 1982 at just 52 years old. Yet, in a tragically short career, he accomplished what few ever will. He gave the modern city a new vertical scale. By challenging the old way of shaky material-heavy frames and replacing them with his revolutionary tube systems, Khan didn't just build taller, he built smarter. From the tapering silhouette of the Sears Tower to the iconic X-braces of the John Hancock Center, his methods invigorated the engineering profession and established the gold standard still used by designers today. As the Engineering News Record noted, while his life was brief, his structures will stand for years, and his ideas will never die. Every time we look up at a modern skyline, we are looking at the enduring genius of Fazlur Khan.